Assalamu alaikum dear students, this is lecture number 12 of week 6, and today's topic is differential amplifier. This is section 10.2 of chapter 10 operational amplifiers of the book electronic devices and circuit theory. In last class we have started operational amplifier. So operational amplifier is available in a package or in the form of an IC having certain number of pins. So this is an IC of a 741 op-amp. This is the pin configuration of the 741 op-amp, and this is the symbol of the op-amp, in which you have two input terminals. One is the output terminal, and we have two supply terminals. One is plus supply voltage and the other one is negative supply voltage. And you can see in the pin configuration here, these are the input terminals, pin number 2 and 3. Pin number 6 is the output terminal. Pin 7 and 4 are supply terminals. The rest of the pins, in which pin 1 and 5 are used to offset null. These pins, the purpose of these pins we will see later. And pin number 8 has no connection with the internal circuit. So this is the internal circuit of 741 op-amp, in which we have this is the input stage, and this one is the output stage. The input stage is a differential stage that we would try to study in today's class. This is of kind this, having two transistors in which these two inputs are applied at the input stage, and this is pin number 2 inverting and pin number 3 non-inverting. This is the output stage, and the output is taken from pin number 6. Pin number 7 is connected with plus supply voltage, and pin number 4 is connected with negative supply voltage. And these are the pin 1 and 5, and they are offset null pins. And you cannot see pin number 8 connected with this circuit. So pin number 8 have no connection with the internal circuit of the op-amp. So this is the differential amplifier. Differential amplifier is the input stage of an operational amplifier, and this differential amplifier consists of two identical branches, which consists of a transistor and a resistor. In this branch we have a transistor and a resistor, and these two inputs that goes to the input of an amplifier, and they are basically at the basis of these transistors. These are the inputs of the amplifier, and these are the two outputs of a differential amplifier. And for a differential amplifier we have two inputs, but for an operational amplifier we only take one output. So any of these two outputs can serve as an output of the amplifier. Either you take output from this terminal, or you take output from this terminal. So we will take in this discussion we would be taking output from this point, the output 2, and inputs are applied as VN1 and VN2. So differential amplifier is basically this is the structure of a differential amplifier. These two branches are identical, and emitter of both transistors are connected to a common point and common resistance, and then we connect two power supplies. One is plus VCC, another is minus VEE, and this differential amplifier is a very popular circuit used at input stage of an op-amp. In every op-amp, input stage is always a differential stage, and this stage can be implemented with either BJTs or MOSFETs, and in each case a pair of transistors is used. So in differential amplifier, both transistors are symmetrical, that is of same number and type, both are NPN and of same beta value. So these two transistors are identical, they have same beta values and they would be symmetrical. Similarly, these two resistors should be of same value, and these two power supplies should be of same magnitude. For a BJT as an input stage, the base terminals of transistors serve as inputs. So input signals which are required to be amplified are connected at the transistor bases, and so for a differential stage there can be two separate inputs and two separate outputs, but you can take any one of these two outputs as the output terminal of an op-amp. So many differential circuits are biased with two DC supplies. However, the circuit can also be operated with one power supply as well. So in this class we would like to analyze the circuit and want to see the operation of the circuit, and to try to determine try to understand the working of this differential amplifier. So towards that we would like to find out the gain of the amplifier, gain to either input or the differential gain and common mode gain of the amplifier. So if you have an op-amp with two inputs, we would like to see what is the differential gain of this amplifier, what is the common mode gain of the amplifier. Towards that we would be interested in analyzing this circuit to find out these quantities. So for that what we do is we first DC bias the circuit. So DC biasing is done with these power supplies, and the purpose of these two power supplies is to set an operating point to turn these transistors on and operate it in the active region. So first what we do is we set these two inputs at 0 and then compute the Q point of the circuit. And so for Q point we would like to find out all the currents in the transistors and all the collector to emitter voltages of the transistor, which are the Q point values. So first what we do is we do a DC analysis, and then we will perform AC analysis to determine the AC quantities like differential gain and common mode gain. So let me do DC analysis first. So for that set input signals at 0. So both input signals are set at 0. So which means that voltage at base of the transistors would be 0 volts. So if the transistor is in active region, then voltage between base and emitter would be 0.7 volts. First we can see that for a transistor to be in the active region, the base voltage should be more positive than emitter voltage. Base voltage should be higher than the emitter voltage. So you can see that emitter is connected with negative supply and base is connected to ground. So it means base would be at higher potential than emitter. So this transistor would be in active region. Similarly, this would also be in active region. So if the transistor is in active region, then there would be IB flowing in the transistor. There would be emitter current. There would be a collector current of this transistor and this transistor as well. So if we want to compute the emitter currents and collector currents, but first you see that as the base emitter voltage is 0.7 volts, the voltage between these two terminals is 0.7, and if I know the voltage at base, I can find the voltage at emitter, because potential difference between these two terminals is 0.7. So potential at emitter would be equal to potential at base minus 0.7. So VE would be equal to potential at base is 0 minus VBE is 0.7. This is then 0 minus 0.7 is equal to minus 0.7 volts. Then if I know the voltage at emitter, which is minus 0.7 volts, then I can compute the value of emitter current by writing the equation for Ohm's law, that is VE minus VEE divided by RE would be equal to IE. So VE is minus 0.7 minus VEE. So VE minus VEE divided by RE would be equal to IE. So this minus and minus becomes plus, so this is plus VEE, and this PE is already computed as minus 0.7. So you will have arrived to this relationship for IE. So if you know IE, you can compute the current in this link and in this link. So the current from this link and this link, they are added to form IE. So IE is split into these two currents. So if these two branches are identical, then current would be divided into half. So IE by 2 would be in this branch and IE by 2 would be in this branch, so that IE by 2 plus IE by 2 becomes equal to IE. So this current would be IE by 2 and this current would also be IE by 2. So these are the emitter currents of these two transistors. So that is emitter current of Q1 is IE by 2 and emitter current of Q2 is also IE by 2. Next is, if you know the emitter current, you can find the value of collector current, as collector current and emitter current are approximately equal. So IC would be equal to IE by 2. Similarly here IC would be equal to IE by 2. So these are the collector currents, and then we can compute the voltage at collectors. So VC1 would be equal to VCC minus IC into RC. So VC1 is equal to VCC minus IC RC, which is also equal to VC2. VC2 is also equal to VCC minus IC RC, where IC is equal to IE by 2. So next we see an example in which these components values are given. Then by using the components values and with the given DC supply voltages, we can compute the values of these DC currents and voltages of the differential amplifier by using the equation derived in the previous slide. So IE would be equal to VEE minus 0.7 divided by RE is 3.3 kilo ohm. So the current would be equal to 2.5 milliampere. So this current is 2.5 milliampere. So half of the current would be flowing here and half of the current would be flowing here. So 2.5 divided by 2 would be equal to 1.25 milliampere. So 1.25 milliampere will be in this link and 1.25 milliampere would be in this link. So these are the emitter currents and are also equal to the collector currents. The collector current would also be equal to 1.25 milliampere. So if I know the collector current, I can find the collector voltage VC1 and VC2. VC1 and VC2 are equal, so they would be equal to VCC minus IC into RC, and VCC is 9 volt minus IC into RC is 3.9 kilo ohm, would result in 4.1 volts. So collector voltage would be at 4.1 volts. Emitter currents are 1.25 milliampere and collector currents are also 1.25 milliampere. So, so you can also compute the value of base current as well by just applying the equation of currents in a transistor, that is I is equal to IC plus IB. So so next is AC operation of the differential amplifier. So in order to perform the AC analysis, so we start in a way that we will consider one input at a time, then apply superposition to get the total output. So when we perform the AC analysis, we consider these voltages to be 0, so they are short circuited, and then because we have two inputs, we can consider one input at a time and then apply superposition to get the total output. So now we can take output from any of the two output terminals. So we will take output from the second transistor's collector. So if I take output from the collector of transistor Q2, that is collector of Q2 serves as the output of the amplifier, then with the application of superposition, let me consider first the input 1 and set the input 2 to 0. So now let input 1 voltage is going positive. So if voltage at the base terminal increased, then what happens is the base current also increases. If base current increases, then emitter current also increases, and if emitter current increases, then collector current would also increases. So with any increase in voltage at the base of Q1, the collector current of Q1 will increase, and if collector current increases, the voltage here at the collector of Q1 will decrease. Now so for the time being, if we assume that this current remains constant, that is it is not changing, which we will see that actually this would happens, that for this case the current remains constant and is unaffected. सो अगर हम थोड़ी देर के लिए ये मान लें कि ये करंट कांस्टेंट है, तो अगर बेस करंट इंक्रीज़ होगा तो एमिटर करंट भी इंक्रीज़ होगा, और अगर ये करंट कांस्टेंट है तो इट मीन्स कि ये जो करंट है ये डिक्रीज़ होगा, क्योंकि अगर ये करंट इंक्रीज़ हो रहा है और ये करंट कांस्टेंट रह रहा है, तो इसका मतलब कि कॉरस्पॉन्डिंगली ये करंट क्या होना चाहिए, ये डिक्रीज़ होना चाहिए, ताकि जितना इसमें इंक्रीज़ है उतना ही ये डिक्रीज़ होगा, तभी ये करंट कांस्टेंट रहेगा। सो अभी अगर हम ये कंसिडर कर लें फॉर द टाइम बीइंग कि ये करंट कांस्टेंट है, तो जितना आप बेस यहाँ पे इनपुट से इंक्रीज़ करने से बेस करंट इंक्रीज़ होगा, कॉरस्पॉन्डिंगली एमिटर करंट भी इंक्रीज़ होगा, और एमिटर करंट जितना इंक्रीज़ इस साइड पे आएगा उतना ही इस साइड पे करंट डिक्रीज़ करेगा। सो अगर ये करंट डिक्रीज़ करता एमिटर करंट, तो इसका मतलब है कि साथ ही कॉरस्पॉन्डिंग कलेक्टर करंट भी डिक्रीज़ करेगा। सो अगर कलेक्टर करंट डिक्रीज़ करेगा तो व्हाट अबाउट दिस वोल्टेज, कलेक्टर वोल्टेज, सो कलेक्टर वोल्टेज इफ करंट डिक्रीजेस दिस वोल्टेज विल इंक्रीज। सो यू सी दैट an increase in voltage on input 1 corresponding increase in voltage at the output of our terminal of the op-amp. So output terminal के ऊपर जो voltage होगी वो correspondingly increase होगी अगर इस साइड पे voltage में increase करता हूँ। Similarly अगर मैं इस साइड पे input अप्लाई करता हूँ और इस साइड पे ग्राउंड करता हूँ, और यहाँ पे मैं वोल्टेज मेरी इंक्रीज़ होती है, तो इसका जो बेस करंट है वो इंक्रीज़ होगा, कोरस्पॉन्डिंगली एमिटर करंट भी इंक्रीज होगा, और अगर ये करंट मैं कांस्टेंट कंसिडर करूँ तो ये करंट डिक्रीज होगा। सो इस करंट के इंक्रीज होने की वजह से कलेक्टर करंट भी इंक्रीज होगा, और कलेक्टर करंट के इंक्रीज होने की वजह से आउटपुट जो है वो डिक्रीज होगी। सो इस टर्मिनल की वोल्टेज इंक्रीज करने से आउटपुट की वोल्टेज डिक्रीज कर रही है, जबकि इस टर्मिनल पर वोल्टेज इंक्रीज करने से आउटपुट इंक्रीज कर रही है। सो इट मीन्स कि अगर मैं यहाँ सिग्नल देता हूँ और यहाँ से आउटपुट लेता हूँ, तो चूँकि इनपुट के इंक्रीज करने से आउटपुट भी इंक्रीज कर रही है, इसका मतलब है कि ये नॉन इन्वर्टिंग टर्मिनल होगा। इसको नॉन इन्वर्टिंग टर्मिनल कहेंगे, क्योंकि इसका जो गेन है वो हमें पॉजिटिव गेन मिलेगा, क्योंकि पॉजिटिव गेन में जो इनपुट और आउटपुट जो है वो प्रोपोर्शनली चेंज होते हैं। इनपुट बढ़ाने से आउटपुट भी बढ़ती है। इस तरह से इनपुट बढ़ाने से अगर आउटपुट कम हो रही है तो इसका मतलब है कि ये जो इसका जो गेन होगा वो नेगेटिव होगा। सो पहले लेक्चर में मैंने आपको बताया था कि अगर मैं पॉजिटिव टर्मिनल के ऊपर इनपुट देता हूँ, अगर मेरे EV1 नॉन इन्वर्टिंग टर्मिनल है और मैं लेट से आउटपुट इस टर्मिनल से दे रहा हूँ, तो जो आउटपुट आएगी दैट वुड बी गेन इनटू इनपुट, गेन वुड बी पॉजिटिव। और अगर मैं इसके ग्राउंड करके इस टर्मिनल के ऊपर इनपुट देता हूँ, तो आउटपुट जो मेरी होगी वो माइनस AD इंटू VD, AD इंटू V इंटू हो जाएगी, जो गेन होगा वो नेगेटिव होगा। सो V इंटू पे जब मैं सिग्नल दूंगा तो आउटपुट के ऊपर गेन, आउटपुट के ऊपर वोल्टेज डिक्रीज करेंगे और मेरा गेन जो होगा वो नेगेटिव होगा, और इसके ऊपर दूंगा इस टर्मिनल के ऊपर गेन पॉजिटिव होगा। Similarly, in this slide it is showing that if input is increasing at V1, output would also increase, and if input is increasing at V2, output will decrease. So for one terminal it is showing increase in output, and for the other terminal it is showing decrease in the output. So for this gain is positive, for this gain would be negative. This we have already said that for AC and AC will be carried out with the, we will consider one input at a time, then we apply superposition. So again we can see this same phenomena where if I apply an input signal at V1, at the output I will get an amplified output, and these two signals would be in phase. So output would be equal to gain into input V1, gain into V1, and gain is some positive value. Similarly for this second input, if I apply the same input signal, I will get an inverted output. With this inverted output shows that the gain is negative. So same gain signal would be amplified with the same value, but now the gain would be negative. So differential next is we are going to determine the differential gain of the amplifier. So in the next slide we are going to compute the differential gain of the amplifier. For that we are going to apply differential inputs to either input terminals with no common mode component. So for finding differential gain of the amplifier, the common mode component should be 0, that is VC should be 0. So VC would be 0 if we have only the differential component of the input signal. So in order to have the differential component only and common mode signal 0, we are setting the V in 1 is equal to Vs by 2, and V into is equal to minus Vs by 2, so that differential voltage would be equal to Vd is equal to V in 1 minus V into, which is equal to V in 1, which is equal to Vs by 2 minus Vs by 2, and it would be equal to Vs, and the common mode signal would be equal to V in 1 plus V in 2 by 2, and that would be equal to 0. Again, AC analysis performed by applying superposition. So for that we consider one input at a time and set the other input to 0. Then we would repeat the analysis for the second input by setting the first input 0. So let me take the differential amplifier with one input applied, that is V in 1, and this is the AC equivalent circuit corresponding to this amplifier. So let me focus on this AC equivalent circuit, in which we have two transistors, and these are the two RE models of corresponding to these two transistors. One is the dynamic resistance and dependent current source for this transistor, and this is the dynamic resistance and dependent current source of the second transistor. This resistance RE is common between these two emitters and connected to ground, because this supply goes to 0. And then we have these two collector resistors, one is here and the second one is here, and they are connected at the collector terminals of these two transistors, and the other terminals goes to ground, because this upper DC supply also set to 0 and becomes grounded. So these are the grounds, and this one is the input signal applied here, and this base terminal of the second transistor is at ground, so V into 0. So अभी अगर हम इस AC इक्विवेलेंट सर्किट को देखें तो इसमें जो AC सिग्नल अप्लाइड है, इस AC सिग्नल की वजह से जो रिजल्टिंग करंट्स फ्लो करेंगे वो भी AC क्वांटिटीज़ हैं. So these are the AC quantities. This is IB1 of the transistor Q1, and इसकी वजह से जो यहाँ पे करंट फ्लो करेगा दैट वुड बी एमिटर करंट, और जो यहाँ करंट फ्लो करेगा दैट वुड बी कलेक्टर करंट. सो कलेक्टर करंट एंड बेस करंट वुड रिजल्ट इन एमिटर करंट here. Similarly for the other transistor, this would be the base current, and it would be negative. I will explain you why it is negative. And this is the collector current that would flow here in the from right to left. It would also be negative. So this arrow would be upward actually, and this is the emitter current. So collector current would be upward, and emitter current would also be upward. So base current would be upward, so emitter current would be in this direction from top to bottom, so that emitter current would be equal to collector current plus base current. So let me explain you the levels of this current and the directions in the figure. In this figure. So अगर हम इस साइड के ऊपर सिग्नल अप्लाई करते हैं और इस सिग्नल को मैं अगर इसकी वैल्यू को मैं इंक्रीज़ करता हूँ, तो जब इनपुट वोल्टेज इंक्रीज़ होगी इसके से ये करंट भी बेस करंट भी इंक्रीज़ होगा. सो अगर बेस करंट इंक्रीज़ होगा तो एमिटर करंट भी इंक्रीज़ होगा. और जो ये वोल्टेज है, इस वोल्टेज को अगर मैं देखूं तो अगर बेस की वोल्टेज इंक्रीज़ होती है तो ये एमिटर की वोल्टेज भी इंक्रीज़ होगी. उसकी रीज़न क्या है? उसकी रीज़न ये है कि जो बेस और एमिटर के जो दरमियान जो वोल्टेज है 0.7 वोल्ट्स वो फिक्स रहेंगे, वो कांस्टेंट है, वो इंक्रीज़ नहीं होंगे. तो यहाँ की वोल्टेज में बढ़ाते जाएंगे तो करस्पॉन्डिंगली ये वोल्टेज भी इंक्रीज़ होते जाएंगे. सो अगर ये वोल्टेज इंक्रीज़ होंगे तो जो ये वोल्टेज फिक्स है तो इसके दरमियान जो पोटेंशियल है वो डिक्रीज़ होगा। अगर ये पोटेंशियल डिक्रीज़ होगा तो जो इसका जो करंट है बेस एमिटर करंट वो भी डिक्रीज़ होगा। सो बेस एमिटर वोल्टेज अगर मैं डिक्रीज़ करता हूँ, अगर डिक्रीज़ होता है तो इसकी वजह से जो बेस करंट है वो भी डिक्रीज़ होगा और एमिटर करंट भी डिक्रीज़ होगा। सो आई एम शोइंग द डिक्रीज़ इन द करंट बाय नेगेटिव साइन। इट मीन्स के जो करंट है दैट हैज़ द डायरेक्शन opposite to this one. So current would decrease and it would signal current would be in the opposite direction. So if this current increases, this current will decrease, and you can say that current in this resistance would be equal to 0. You can see this current, entering current is negative, this current is positive, the sum of these two current would be 0. So the current in the emitter resistance would be 0. It means voltage is 0 at this terminal. So if this current is 0, it means the potential here is not changing. That's why if this current remains at 0, the only possibility is the potential remains constant at this point. And if this current is 0, then this current and this current would be equal because sum of these two currents would be 0. So direction of this current IE would be this one, and would be emitter current of second transistor would be of direction similar to IE. So IE would be up in the direction entering into the emitter. So this current is IB1 and this current is IE1. This IE1 would be equal to IE2, and the direction of IB2 is negative, and that's why IE is entering into the emitter of the transistor. So IB1 would be equal to IB2, would be equal to IB. These two currents IB1 and IB2 would be equal in magnitude because we are assuming that these two transistors are identical. So if these two transistors are identical, then the currents would be same in magnitude. Similarly, if these two currents are equal, then RE1 would be equal to RI1 is equal to RI2, which is equal to RI, and RI low is equal to beta RE. So for RE very large, ideally infinite, the circuit for obtaining the KVL equations simplifies to that shown in figure 10.16, from which we can write. So if this resistance is very large, then this current would be approximately 0, and IB1 would be equal to IB2, and it would be equal to IB. So these currents are equal, and you can write this equation as V in 1 would be equal to IB into RI. This is voltage drop, IB into RI, and this is the second drop, IB into RI2, which is RI, equal to 0. From this equation these two can be added, so this becomes minus 2 IB into RI, and from which I can find IB would be equal to VI1 divided by 2 RI, and with RI is equal to beta RE, so VI divided by 2 into beta RE. So if we also assume that beta 1 is equal to beta 2 is equal to beta, then IC would be equal to beta IB. If I computed IB, then I can also compute IC by assuming the beta of the transistors are equal, then IC would be equal to beta IB. And by plugging the value of IB from the last slide, IB was equal to VI divided by 2 into beta RE, and beta can be cancelled, so IC would be equal to VI divided by 2 RE. And the output voltage magnitude at either collector would be equal to, output would be equal to IC into RC. So this is the output, which would be equal to the current in this resistance, which is IC into RC. So this current is negative, which means the actual current is flowing from top to bottom, so voltage would be positive and would be equal to IC into RC. So IC into RC, and IC is equal to V over 2 RE and into RC. So from here I can compute V out over V in, that would be equal to RC over 2 RE. So RC over 2 RE would be the gain of the amplifier. Next is this is the output voltage. This is the output voltage due to V in 1 only. Similarly, we can compute output voltage due to V in 2, and that is called V out 2, and then let V in 1 is equal to V in 2 equal to Vs by 2. Then V out 1 would be equal to RC divided by 2 RE into Vs by 2, and V out 2 would be equal to minus Vs by 2, and this minus becomes plus, so this also becomes equal to plus RC over 2 RE into Vs by 2. So if I have arrived for the outputs due to the individual inputs, then total output would be by superposition sum of these two outputs, V out 1 and V out 2. So V out would be equal to sum of these two expressions, and from which after simplification I will get V out equal to RC over 2 RE into Vs. So this if I compare this relationship, then I can write it as this is the gain of the amplifier and this is the VD. So gain into VD is called the output, where VD is equal to V in 1 minus B into, and V in 1 is Vs by 2, and V into is minus Vs by 2. So VD would be equal to Vs, this is VD, and this is the corresponding gain of the amplifier. So from here we can say that the gain of the amplifier is nothing but RC over 2 RE, and this is called the differential gain, and its value will be large, because you can choose a large value of resistance RC, and that is typically in kilo ohms, so this gain turns out to be a large quantity. And next is what is common mode operation of the circuit. So gain to the common mode inputs should be small. When you apply same signal at the both inputs, then this signal should not amplify at the output. Let's see how. So you can see that in previous slides for differential amplifier we have seen that if I apply input at this point and take output here, then I will get a positive gain, and signal would be in phase, and I will get a in phase output, amplified output. Similarly, if I apply input here of same value, then I will get an output here where that would be inverted. So this red one would, I will get signal when I applied input here, and these two would have the same gain. For this input I will get the same amplified output as for this input. So if I add these two outputs, this blue one and red one, I will get output 0. So as we are applying a superposition to get the output. So I can write for the common mode case as V out 1 would be equal to gain into V in 1. Gain is positive, and for second input V out 2 would be equal to gain into input 2, and gain is negative. And if I set V in 1 and V in 2 equal, so and are equal to Vs, then this becomes Vs, this is also Vs. So V out 1 would be equal to this much into Vs, V out 2 would be equal to this much into Vs, and by superposition output equal to sum of these two. So if I add this one and this one, I will get output 0. So for the common mode signals, I will get 0 output for the differential amplifiers. That is, this amplifier doesn't amplify the common mode signals. So for common mode operation, you will not get any output for the common mode input, but for common mode operation, output will be 0 as Vd is equal to 0, but we will get some output due to the common mode input, and there will be some common mode gain of the amplifier as well. So next we see how much this gain would be. So before going to the AC analysis to determine the common mode gain, let we see the impact of applying the inputs of the same magnitude at the both inputs, that is the common mode case. So if I apply voltage at this point and at this point of same value, then with the application of voltage at this point, the current IV will increase and corresponding emitter current will also increase. And if I apply same potential at this terminal as well, then corresponding to this potential, there would be a same increase in IB and same increase in IE as for this side. So these two currents would be equal and of same direction. So अगर मैं यहाँ पे भी वोल्टेज इंक्रीज करता हूँ और सेम ऑर्डर पे इस साइड पे भी वोल्टेज इंक्रीज करता हूँ, तो जो करंट होंगे एमिटर करंट वो उसकी डायरेक्शन इस ट्रांजिस्टर में इस डायरेक्शन में करंट फ्लो करेगा एमिटर करंट, और इस ट्रांजिस्टर में भी एमिटर करंट की ये डायरेक्शन होगी. सो इस पॉइंट के ऊपर ये दोनों करंट्स ऐड अप होंगे और इस रजिस्टर में जो करंट फ्लो कर रहा है दैट वुड बी सम ऑफ दीज टू करंट्स. सो इफ अगेन आई assume this resistance very large, then these two currents will be sum of these two currents when it flows through this resistance, then this current magnitude of this current would be very small, because if resistance is very large, then current magnitude would be very small. So because of the fact that this resistance emitter resistance is applied here is kept very large, so as a result the magnitude of the current through this resistance would be very small. It means if this current is very small, then potential here would not change very drastically, and there would only be a slight change in the potential here. So if this potential is not changing, it remains pretty constant, then as a result the currents in these transistors would not be varying, and if these currents are not varying, then the voltage would also remain constant at the collector, and there would be only a small change in the collector voltage. And so because of the application of the common mode signals, the output voltage would not change much, and the common mode gain would be very small. So this is the AC equivalent circuit for the common mode case, and in which the input signals which are common to both inputs, same signal is applied at both inputs, And again, this is the RE model of the transistor 1 and RE model of transistor 2, and these are the collector resistances, and this is the emitter resistance. In this case, this is IB entering in this direction, and this is also entering into the base, and these are the emitter currents, beta plus 1 IB and beta plus 1 IB, and at this point these two currents are adding and becomes equal to 2 into beta plus 1 IB. So from the sequence circuit we can write the equation for the base current as IB would be equal to V in minus this is V in minus this potential minus this potential. This potential is same as this potential, and this potential is equal to 2 into beta plus 1 into IB into RE. This is the current into resistance would be equal to this potential. So this potential would be equal to this current 2 into beta plus 1 IB into resistance. So this is the potential V in minus this potential divided by RI, and RI is this resistance. The potential here minus potential here divided by RI would be equal to IB flowing through this RI. So if we have this equation, then from this equation we can rewrite this equation as by taking common by solving this equation for IB, we will have IB would be equal to V in our RI plus 2 into beta plus 1 RE. So then we can find out the output voltage magnitude, that would be equal to V out is equal to IC into RC, and if I know IB, then I can find out IC by beta IB. So this beta IB into RC, and by plugging the value of IB from this equation, I will get a relationship for V out equal to this, and from which I can find out V out over V in, and V out over V in equal to beta RC over the numerator, sorry, denominator of RI plus 2 into beta plus 1 R. So this is the common mode gain of the amplifier. So for example, calculate the common mode gain of the amplifier for this circuit shown in figure 10.17 of example 10.3. Then by using the above equation, I can plug the values of the circuit, in which we are given with beta equal to 75 and RC is equal to 47 kilo ohm, and from which RI I can compute as 20k, that is given in the example, and by plugging the values of beta and RE, we end up with the gain of value 0.54. So this is the common mode gain of the amplifier, which is pretty less than 1, which is 0.54, and for differential gain you will get you can use this relationship for the differential gain, and it would be quite large as compared to the common mode gain. So that's it for today's class. We will continue from this point in the next class, inshallah. Thank you.